My name is K. Sai Chon. I am from ITB section. Today's topic is characteristic vector. Introduction to characteristic vectors. Characteristic vectors are fundamental in various mathematical and computational contexts. They represent specific properties or features of mathematical objects such as matrices or geometric figures. Understanding characteristic vector is essential for fields like linear algebra, statistics, and machine learning. Then, vector properties, types, and characters. Then, definition of characteristic vectors. A characteristic vector, often called an eigenvector, is associated with a square matrix. It is non-zero vector that changes only by a scalar factor when a linear transformation is applied. The corresponding scalar is known as the eigenvalue, which provides insight into the matrix behavior. Mathematical representation. The relationship can be mathematically expressed as AV is equal to lambda, where A is a matrix, V is a characteristic vector, and lambda is the eigenvalue. This equation states that applying the matrix to vector V results in a scaled version of V. Finding characteristic vectors involves solving the characteristic equation. Finding characteristic vectors. To find characteristic vectors, one typically starts by computing the eigenvalues of the matrix. Once the eigenvalues are known, substitute them back into the equation A minus lambda to find the corresponding vectors. This process may involve row reduction or other linear algebra techniques to solve the resulting system of equations. Applications in physics. As we know, mathematical equations are also applicable in physics. Characteristic vectors play a significant role in quantum mechanics, particularly in the study of wave functions. They help identify stable states of a quantum system corresponding to measurable quantities. The eigenvalues associated with these vectors can represent energy levels of the system. Next, applications in engineering. In engineering, characteristic vectors are crucial for analyzing systems stability and control. They help in designing systems to ensure desired performance and response characteristics. Eigenvalues derived from characteristic vectors can indicate system resonance or natural frequencies. Definition of characteristic polynomial. Characteristic polynomial, suppose V is a complex vector space and let lambda 1, lambda 2, lambda n denote the distinct eigenvalues of T with multiplicates given the polynomial z minus lambda 1 to n is called the characteristic polynomial of T. Applications in computer science. In computer science, characteristic vectors are used in machine learning for feature extraction. They help in dimensionality reduction techniques such as principal component analysis (PCA). By focusing on characteristic vectors, algorithms can identify the most significant features of data. Feature extraction method. Data scientists leverage characteristic vectors to improve model accuracy and efficiency. They can extract latent features within data sets, enhancing predictive performance. Understanding the structure of characteristic vectors aids in data visualization and interpretation. In the image you can see two matrices are multiplied, and the process they were multiplied we can see in the image. Types of characteristic vectors. Characteristic vectors can be categorized based on their properties and applications. Some common types include simple, complex, and generalized eigenvectors. Each type provides unique insights depending on the context in which they are used. Types of personality: sanguine, choleric, melancholic, phlegmatic. Simple eigenvectors. Simple eigenvectors correspond to distinct eigenvalues and are straightforward to compute. They provide a clear representation of the linear transformation associated with the matrix. These vectors are particularly useful in systems with unique solutions and straightforward dynamics. Next, complex eigenvectors. Complex eigenvectors arise when the matrix has complex eigenvalues, often seen in oscillatory systems. They can provide insights into systems that exhibit rotational or oscillatory behavior. Analyzing complex eigenvectors is crucial in fields like control theory and signal processing. In the image, they have given a vector A. The character polynomial is lambda square minus 8 lambda plus 17. So the eigenvalues of A are lambda is equal to 8 plus or minus root minus 4 by divided by 2 is equal to 4 plus or minus 8. Generalized eigenvectors. Generalized eigenvectors are used when matrices have repeated eigenvalues and insufficient eigenvectors. They help from a complete basis in cases where simple eigenvectors cannot fully describe the system. Understanding generalized eigenvectors is essential in advanced mathematical theories and applications. Then, characteristic vectors and matrix diagonalization. Characteristic vectors are key to diagonalizing matrices, simplifying complex linear transformations. Diagonalization allows for easier computation and analysis of matrix powers and functions. This process is vital for solving differential equations and other mathematical problems efficiently. Then, numerical methods for characteristic vectors. Finding characteristic vectors can be computationally intensive, requiring efficient algorithms. Numerical methods such as QR algorithm and power iteration are commonly employed. These techniques facilitate the computation of eigenvalues and eigenvectors for large matrices. Then, visualization of characteristic vectors. Visualizing characteristic vectors can provide intuitive insights into their properties and behavior. Graphical representations help in understanding the relationships between different vectors. Tools such as scatter plots and vector fields are useful for visualizing these concepts. Then, challenges in working with characteristic vectors. One major challenge is dealing with numerical instability in computations for large matrices. Another issue arises when working with matrices that have close or repeated eigenvalues, complicating the extraction of vectors. Third one, understanding these challenges is key to improving accuracy and reliability in application. Case study: characteristic vectors in machine learning. In machine learning, characteristic vectors are used to identify patterns with high dimensional data. They help in reducing noise and improving model performance by focusing on significant features. Case studies demonstrate the effectiveness of characteristic vectors in various predictive tasks. Future directions in research. Ongoing research explores advanced methods for calculating and applying characteristic vectors. Innovations in machine learning and AI are likely to enhance the role of characteristic vectors. The intersection of characteristic vectors with other mathematical disciplines continues to reveal new insights. Summary of key points. Characteristic vectors are essential tools in mathematics, physics, engineering, and data science. They provide valuable insights into the behavior of linear transformation and systems. Understanding their properties and applications is crucial for advancements in technology and science. Conclusion. Characteristic vectors are foundational concepts in various fields, influencing both theory and practice. Analyzing these vectors can lead to improved solutions for complex problems. Continuous exploration of characteristic vectors will yield innovative approaches across disciplines. Then, references. Linear algebra and its application. Linear algebra and its application 5th edition and 4th edition are very useful for characteristic vectors. Thank you.